the AI Competence Plus Compliance podcast, artificial intelligence for decision makers, efficient, understandable, and completely bullshit-free.
This podcast is for information and entertainment purposes and does not constitute legal advice. The voices in this podcast were generated using AI.
Welcome back to this deep dive, our ongoing exploration into the crucial and, let's face it, quickly changing world of AI competence and compliance.
It really is moving fast. It's a landscape that demands attention, especially, as new regulations like the AI Act start to take shape.
Absolutely. And today we're diving deep into a vital new resource designed to help cut through some of that complexity. The book, AI Act Competence Plus Compliance Fundamentals of Artificial Intelligence and Its Safe Use in the European Union by Marcus M. Kirchmayr.
Well, that sounds incredibly timely. A comprehensive guide is definitely needed right now for anyone grappling with AI.
It truly is. It's brand new, just published in May 2025, so it's very current. You can find it now in bookstores and also online at iac-book.eu.
Good to know.
And what I think is particularly valuable is that it's written to equip, pretty much everyone involved in AI, from entrepreneurs and executives right down to the people actually using the technology and even HR developers thinking about skills.
That's a really important approach. AI doesn't just live in the tech department, does it? It impacts so many roles.
Exactly. It gives them the essential knowledge for responsible AI implementation, specifically within the framework of the European AI Act.
That legal context is key.
Totally. And for this deep dive, we're zoning in on Chapter 2, Fundamentals of Artificial Intelligence. This chapter really lays the critical groundwork. It explains, what AI is, how it works, and introduces the core ideas we'll need as we explore the book and the regulations further.
Setting the stage, basically.
Right. Our goal today is just to unpack these fundamentals and maybe highlight the insights that are most relevant and useful for you listening. Okay, so the book kicks off right away trying to define AI. What's the core idea it presents there?
Well, the book starts pretty broadly, explaining AI as technologies and systems that can perform tasks that traditionally you'd need human intelligence for.
Okay, like what kind of tasks?
Think about things like learning from experience, spotting really intricate patterns in data, and making decisions autonomously without direct step-by-step instructions.
So it's essentially about enabling machines to handle tasks we usually associate with, human thinking.
Precisely. And it emphasizes that AI is a major field within computer science, really focused on creating systems that can, mimic or automate intelligent behavior.
Right.
The chapter also gives some crucial historical context, which I think is helpful. It mentions Alan Turing's famous Turing test from way back in 1950.
The imitation game idea.
Exactly. That test asked a really fundamental question. Could machines ever convincingly imitate human conversation to the point where you couldn't tell the difference? It's a benchmark that still sparks discussion today, actually.
Yeah, the idea that you might not know if you're talking to a machine or a person, it still feels pretty sci-fi sometimes. And then the book mentions the Dartmouth Conference in 1956. Why was that so significant?
Dartmouth. That's really where the term artificial intelligence was officially coined by John McCarthy. He defined it as the science and engineering of making intelligent machines.
So that was the formal birth, so to speak.
Pretty much, yeah. That conference is widely seen as the formal starting point for AI as an academic discipline. It really set the stage for, everything that followed.
It's fascinating to think about that foundational moment. And the book traces how AI has evolved since then, right? From those early, maybe simpler rule-based systems to the much more dynamic approaches we see now.
Yes, absolutely. Early AI systems relied heavily on these fixed rules and logical algorithms. They were good for certain specific problems, like playing chess maybe, but their limitations became pretty clear when faced with more complex, unpredictable real-world situations.
They weren't very flexible.
Not really. The real shift, the one we've seen accelerate in recent decades, is down to two main things: the explosion of available data, just vast amounts of it, and the massive increase in computing power. This combination has allowed for the development of much more flexible, self-learning systems.
So while McCarthy's original definition sort of provides a foundation, the way AI actually achieves intelligence has changed dramatically. The book then breaks down the fundamental ways AI operates. What are the key mechanisms it talked about?
According to the chapter, there are 4 core operational concepts: intelligence, learning, problem-solving, and decision-making.
Okay, let's take those one by one. Intelligence first.
Right. Intelligence in this AI context refers to the ability to take in information, discern patterns within it, sometimes very subtle patterns, and then draw conclusions or make informed choices based on that. AI systems can now automate complex tasks like identifying these patterns in massive data sets or making forecasts based on trends.
That makes sense, seeing the underlying structure and maybe anticipating what might happen next. And the second concept is learning, which I guess is where machine learning comes in.
Exactly. Machine learning is key here. The book contrasts this sharply with traditional software, which, operates based on fixed pre-written instructions.
Like a script it has to follow.
Precisely. AI, through machine learning, can analyze huge amounts of data, independently find relationships and patterns within it, and actually improve its performance over time without needing to be explicitly reprogrammed for every new scenario. This capacity to learn and adapt is what makes modern AI so powerful and versatile.
Right, so it's not just following a fixed path, it's constantly refining its own approach based on new information it sees. What about problem solving?
Here the book explains that AI employs various techniques to tackle complex challenges. It might use things like heuristic search, kind of smart guessing, apply logical reasoning, or work on finding optimal solutions. Think of a program that can play a really complex game, like Go and come up with novel strategies on its own.
Okay, like figuring out the most effective way to achieve a goal in a complex situation. And finally, decision making.
Yeah, this refers to how AI systems make choices based on the data they've processed and the algorithms they use. They often work by calculating probabilities and systematically addressing uncertainties to arrive at a decision. It's about making data-driven choices in a structured, often automated way.
Okay, so those 4: intelligence, learning, problem solving, and decision making are the fundamental ways AI operates. The chapter also draws a really clear line between AI systems and traditional software. What's the crucial distinction there, boiled down?
The main difference really lies in that ability to adapt and learn. Traditional software works based on a fixed set of rules and produces predictable, predetermined results. If the environment changes or if new requirements emerge, the software needs to be manually updated by a programmer.
Like the example the book uses, an accounting program.
Exactly. It performs its calculations based on the rules it's given, and if tax laws change, someone has to go in and physically rewrite the code.
Right. So how does AI differ in its response to those kinds of changes?
Well, AI systems, especially those using machine learning, can learn from new data and adapt to changing circumstances, often without needing that direct human intervention. The book gives the example of an AI tax forecasting system.
Okay.
It could potentially automatically factor in regional differences or new legislation just by analyzing updated tax data feeds without requiring a programmer to rewrite its core logic every time.
That's a significant advantage, isn't it? That ability to evolve and adjust on its own. And this adaptability naturally leads to AI being applied across a really wide spectrum of fields.
Oh, absolutely. The book highlights several key areas, things like image processing, facial recognition, security monitoring, autonomous vehicles that use real-time sensor data to navigate complex environments.
Self-driving cars, yeah.
Speech recognition and voice assistants like Siri or Alexa that actually get better at understanding you through machine learning. Medical diagnostics, where AI can analyze complex data, like scans, to help doctors make more accurate diagnoses. And even marketing, using AI to create personalized campaigns based on understanding customer behavior patterns.
Wow, it really is becoming integrated into so many aspects of our lives and industries. And it sounds like current research in AI isn't just about making these systems more capable, but also more reliable and maybe understandable.
That's right. The chapter points to ongoing research in areas like optimizing machine learning algorithms, advancing natural language processing so AI can understand us better, and developing what's called explainable AI or XAI.
Explainable AI, so we can actually understand how these systems arrive at their decisions.
Exactly. Trying to open up that black box.
Yeah.
There's also a growing emphasis on practical considerations, like the ethical implications, potential biases, and even the ecological concerns around the resources needed to run some of these very powerful AI models.
Important points as AI becomes more pervasive. Now, the book transitions to a really critical area, especially given the book's title, the legal definition of AI. Why is nailing down a specific legal definition so important?
Well, it's crucial because this definition, specifically the one laid out in Article 3, Paragraph 1 of the European AI Act, determines what actually falls under the scope of the regulation.
So it dictates what rules apply to which systems.
Precisely. It's a very pragmatic definition, really focused on the characteristics that are relevant from a regulatory standpoint. And it might actually differ quite a bit from more academic or general definitions of what constitutes AI.
Okay, so if a system meets this legal definition, it becomes subject to all the rules and requirements of the AI Act. What are the key elements of this legal definition that businesses and developers really need to get their heads around?
The book breaks it down into several important aspects. Firstly, it has to be a machine-based system. That means it relies on some kind of physical or digital infrastructure servers, cloud platforms, sensors, and it excludes purely manual processes.
Makes sense. What else?
Secondly, it's designed to operate with varying degrees of autonomy. This is interesting because it covers a whole spectrum, from systems with very minimal independent action, maybe like a basic chatbot suggesting replies, all the way up to highly autonomous systems like self-driving cars. And this level of autonomy often plays a big role in how the system is classified in terms of risk under the Act.
Okay, so autonomy is a key factor.
Definitely. Thirdly, a really crucial element is adaptiveness after deployment. This is about the system's capacity to learn and adjust its behavior after it's been put into use. Think of a spam filter that gets better over time at identifying new types of junk email based on what users mark as spam.
So it learns on the job, essentially.
You could say that. Fourth, it states that the system infers from the input it receives how to generate outputs. This means it doesn't just passively process data, it actively analyzes it, draws conclusions, and uses those conclusions to produce something new.
Like what kind of outputs?
Well, the definition lists examples like predictions, content, recommendations, or decisions. So it covers a huge range of AI applications.
Right.
And finally, and this is important, these outputs can influence physical or virtual environments. This highlights the real-world impact AI can have, whether it's a robot arm, moving things in a warehouse, physical, or an algorithm personalizing the content you see on a website, virtual. This potential to influence the environment increases its regulatory and ethical significance.
So it's not just about processing information in a vacuum. It's about generating something that can actually have a tangible effect on the world around us, physically or digitally. And the book really emphasizes the distinction between this regulatory view and maybe the more academic focus on simply creating intelligent machines, right?
Exactly. While someone like John McCarthy was focused on the fundamental concept of machine intelligence itself, the AI Act takes a much more pragmatic, regulation-driven perspective. It needs a clear line.
And this legal definition also helps distinguish AI from traditional software again.
Yes, the book reiterates that point. Things like a basic calculator, which performed fixed operations based on rules, clearly lack that ability to learn and adapt, so they wouldn't be considered AI under the Act. Even static expert systems, which operate using rigid if-then rules programmed in advance, are generally exempt.
Okay. And I remember seeing a helpful table in the chapter that summarizes these key differences.
Yes, it's quite useful. It clearly outlines the distinctions based on things like the underlying basis. Is it data-driven or based on fixed rules? Its ability to adapt dynamic versus static, the nature of its output predictions and decisions versus calculations and fixed results, and most importantly, whether it falls under the scope of the AI Act.
Really handy for quickly grasping where those boundaries lie. And the chapter boils it down even further, providing 3 key questions to help determine if a system is likely to be classified as AI under the Act. What are those critical questions?
All right, these are really practical. You need to ask, 1, does the system learn independently from data? 2, can it automatically adapt its behavior after it has been deployed? And 3, does it have the ability to actively influence its environment, physical or virtual?
So if the answer to those is generally yes,
Then it's highly likely that the system will be considered AI under the AI Act and subject to its rules.
and the book gives some practical examples too, right? Comparing things like a standard ERP system to an AI warehouse system.
Exactly. It clarifies that a typical ERP system that just calculates inventory based on fixed formulas wouldn't usually be AI. But an AI system in a warehouse that analyzes complex order patterns, maybe predicts future demand, and optimizes stocking levels based on that learning, that likely would be AI.
And chatbots.
Similar distinction. A simple chatbot with pre-programmed answers following a script, probably not AI under the Act, but a chatbot that learns from conversations, improves its responses over time, maybe even adapts its tone, that would likely be regulated.
That makes the distinction much clearer in practical terms. And the tip in this section seems really important for businesses starting out with AI.
Absolutely critical. The book strongly advises businesses to conduct a thorough and crucially early systematic risk analysis. You need to figure out if your systems fall under the AI Act and understand the potential regulatory obligations you might face. Knowing if your systems are in scope is the fundamental first step towards compliance. Don't wait until it's too late.
Sound advice. Okay, moving on. Chapter 2 then delves into the different types of AI systems. Why is it important for us to categorize AI in this way?
Well, because AI systems aren't all the same. They differ quite significantly in how they function, what they can realistically be used for, and their overall level of, let's say, sophistication or intelligence.
Okay.
Understanding these distinctions is crucial for businesses. First, when they're choosing the right AI technologies for their specific needs, and second, for navigating the AI Act, because different types of AI might be associated with different levels of risk and therefore different regulatory requirements.
Right. The risk classification depends partly on the type. The book starts by differentiating AI based on its level of intelligence, what it calls weak AI versus strong AI. Can you break down the difference there?
Sure. Weak AI, which is also often called narrow AI, refers to AI systems that are designed and trained for a very specific task or a narrow set of tasks. They can excel within their defined domain, sometimes performing better than humans, but they lack general intelligence. They can't really perform tasks outside their specialization.
What are some examples?
Things like the recommendation systems you see on Netflix or Amazon, or automated quality control systems in manufacturing that inspect products for defects. Their strength lies in that focused application, but they need clear goals and high-quality data specifically for that task.
So they're incredibly good at one thing, maybe, but that's the limit of their capabilities. What about strong AI?
Strong AI, also sometimes called artificial general intelligence or AGI, well, it's currently more a theoretical concept. It refers to AI with the ability to understand, learn, and apply knowledge across a wide range of tasks, much like human intelligence. It could, in theory, perform any intellectual task a human can.
That sounds like the AI we see in movies.
Pretty much. The long-term vision, and frankly, it raises significant ethical and regulatory questions that we're only just beginning to grapple with. The book points out, and most experts agree, that we are still quite a ways off from achieving true strong AI.
So for businesses now, the focus is really on narrow AI.
Absolutely. Narrow AI is what's commercially available and relevant for most businesses today. The key insight here is that weak narrow AI solves specific problems really well now, while strong AI AGI is a future goal with really complex implications we need to think about.
Good to keep that future potential in mind, but yeah, the immediate focus is definitely on the AI technologies available today.
The chapter then distinguishes AI systems by their functionality and how they make decisions. Looking at rule-based systems versus learning systems, what's the fundamental difference in how they work?
Okay, so rule-based systems, sometimes called symbolic AI, operate based on a set of pre-programmed rules and logical structures like, if this happens, then do that. They make decisions by applying these explicit rules to the input data.
What are the pros and cons of that?
Well, they are typically very transparent. You can usually trace exactly why they made a certain decision. They're predictable and relatively easy to understand and control. But the downside is they lack flexibility. They can't easily handle situations or data that falls outside the predefined rules. The book gives the example of a simple customer service chatbot that routes inquiries based on keywords. It just follows the script.
Right, it follows a set path but gets stuck if something unexpected comes up.
How do learning systems differ?
Learning systems, which is basically machine learning systems, are designed to learn from data. They identify patterns and relationships within the data itself and then use these learned patterns to make predictions or decisions.
So they build their own rules, in a way.
In a sense, yes. This makes them much more adaptable and powerful, especially for complex problems where the rules aren't easily defined. However, they can also be more opaque, often described as black boxes, because it can be hard to understand precisely why they reached a certain conclusion. This opacity poses regulatory challenges, particularly around transparency and accountability.
Right, that trade-off between adaptability and transparency seems to be a recurring theme, doesn't it?
It really is. A core tension in AI development and regulation. An example here would be an AI system analyzing historical sales data to identify subtle trends and automatically generate sales forecasts, something a purely rule-based system would struggle with.
And the book also discusses hybrid systems, trying to get the best of both worlds.
Exactly. Hybrid systems aim to combine the strengths of both approaches. They might use machine learning to identify complex patterns in data, but then apply a set of predefined, understandable rules based on those patterns to make the final decision.
Where might that be useful?
This approach can be particularly useful in regulated industries like finance or healthcare, where you need both adaptability to handle complex data and transparency to meet compliance requirements. The book mentions medical diagnostic systems as a potential example, using ML to analyze images, but maybe following a documented, rule-based process for the final diagnosis steps.
A way to leverage the power of learning while maintaining some degree of explainability. Okay, finally, in this section, the chapter categorizes AI systems by their application area. This really highlights the diverse ways AI is actually being used out there.
It really does. The book outlines several key application areas, and it's worth noting how these often link back to risk levels under the AI Act. Well, there's generative AI things like ChatGPT or DALL-E that create original content like text and images. These have their own specific regulatory considerations discussed later in the book. Natural language processing, NLP, which deals with understanding and generating human language like in chatbots or translation tools, is often classified as limited risk.
Okay.
Computer vision systems, which analyze visual data like images or video feeds for things like quality control or traffic monitoring, are frequently considered high risk due to their potential impact on safety and security.
Right. If they get it wrong, the consequences could be serious.
Exactly. Similarly, robotics, where AI is integrated into physical robots for tasks in manufacturing or even surgery, is also often deemed high risk for safety reasons. And then you have autonomous systems like self-driving cars or autonomous drones, which make independent decisions in complex environments. These generally face the most stringent regulatory requirements and are typically classified as high risk.
So it's clear that the specific application of the AI significantly influences the level of scrutiny, as well as the technical and data requirements. And the tip in this section is quite practical for businesses trying to choose.
Yes, the book advises businesses to really think about the specific task they need to accomplish and select the type of AI system that's most appropriate. Rule-based AI might be perfectly sufficient and more transparent for simpler processes, whereas learning AI or ML would be more suitable for complex forecasting or analysis where adaptability is really key. It's about matching the tool to the job.
Makes perfect sense. Okay, chapter 2 then moves on to what the book aptly calls the fuel for AI systems.
Yep.
Data. Why is data so absolutely critical?
Well, it's simple, really. Data is the very foundation upon which most modern AI systems, especially machine learning systems, are built and learn. Without high-quality, relevant data, an AI system simply cannot function effectively. It's like trying to run an engine without fuel. For data-driven approaches like machine learning, the data is everything. It's the primary source for learning patterns, adapting to new situations, and even evaluating the system's performance. AI essentially learns by identifying recurring patterns within the data it's given.
So the quality and the amount of this data directly determine how well the AI will perform. It's the classic garbage in, garbage out principle.
Exactly that. The book really stresses the importance of data quality. The data needs to be accurate, complete, up-to-date, and crucially, representative of the real-world scenarios the AI will encounter.
What happens if it's not representative?
If the data is flawed, biased, or doesn't accurately reflect the reality the AI needs to operate in, the AI will inevitably produce skewed, unreliable, or even harmful results. The chapter gives an example of a retail AI trained only on urban consumer data. It would likely make poor predictions or recommendations for stores in rural areas because the training data wasn't representative.
Okay, so quality and representativeness are key. What about quantity? Do you always need massive amounts?
Quantity is important too, yes. Many modern AI models, especially deep learning models, do require large data sets to learn effectively and identify subtle patterns. However, the book also cautions against simply collecting vast amounts of irrelevant data, sometimes called data clutter, which can actually introduce noise and make the learning process less efficient. It's about having enough relevant data.
So having the right kind and the right amount of data is crucial. And data plays different roles throughout the whole life cycle of an AI system, doesn't it? It's not just used once.
That's a key point. The chapter outlines these different roles. There's training data, which is used to initially teach the model the patterns it needs to recognize. Think of sales data used to train a revenue forecasting model.
Okay.
Then there's validation data. This is used during the training process to fine-tune the model's settings, its hyperparameters, and importantly, to prevent it from overfitting.
Overfitting, meaning it learns the training data too well.
Exactly. It becomes too specialized on the training examples and doesn't generalize well to new, unseen data. Validation data helps you check for that and adjust the model.
Got it. And the third type?
Test data. This is a completely separate data set, unseen during training or validation, used to evaluate the final performance of the trained model. It gives you an unbiased assessment of how well the AI is likely to perform in the real world.
Training, validation, testing. Makes sense.
And beyond that, there's also the role of real-time data, which can be used to continuously update and improve the performance of AI systems after they've been deployed, like a chatbot, learning from ongoing customer interactions to get better over time.
So it's not a one-time process of feeding data in. It requires ongoing management and potentially continuous updating. The chapter also distinguishes between different categories of data. What are the main types we should be aware of?
The two primary categories discussed are structured data and unstructured data.
Structured data sounds organized.
It is. Structured data is highly organized, typically stored in tables or databases with clear rows and columns. Think of sales figures in a spreadsheet, customer demographics in a CRM system. This type of data is generally easier for computers to analyze and is well suited for many traditional AI applications, like financial forecasting or analyzing customer purchase history.
And unstructured data?
Unstructured data is, well, less organized. It doesn't fit neatly into tables. It includes things like text documents, emails, reports, social media posts, images, audio files, and videos.
So most of the data we create day to day.
A huge amount of it, yes. While it can be more challenging for AI to process, unstructured data often contains richer and more nuanced information. For example, analyzing the sentiment expressed in customer reviews, text, or identifying objects in security video. The book gives an example of a car manufacturer combining sensor data, structured, with camera images, unstructured, for driver assistance systems.
So structured is like a neat spreadsheet. Unstructured is more like a collection of documents, images, and sounds. And actually getting this data into a usable format for AI must be a significant undertaking in itself.
Oh, absolutely. Data preparation is often one of the most time-consuming parts of an AI project. The book highlights the importance of strategically selecting data sources, internal systems, external feeds, public data sets to ensure the data is representative and relevant.
What else is involved?
Well, for certain types of unstructured data, like images or medical scans, a process called annotation or labeling is often necessary. This involves humans, or sometimes semi-automated tools, adding tags or descriptions to the data to provide the AI with examples of what it's supposed to identify, like labeling tumors in medical images.
Okay, teaching the AI what to look for.
Exactly. And then the raw data typically needs significant processing. This involves cleaning it to remove errors, duplicates, and inconsistencies, normalizing it so different features are on a comparable scale, and potentially performing feature engineering, which is about selecting, transforming, or creating the specific input variables that will be most informative for the AI model to learn from.
Wow, lots of important steps in just preparing the data before the AI even starts learning. And there are also significant challenges associated with using data for AI, aren't there? Ethical and legal ones?
Yes, definitely. The chapter points out some key challenges. One major one is bias. Data can reflect historical biases present in society or in the way it was collected. If an AI learns from biased data, it can perpetuate or even amplify that bias, leading to unfair or discriminatory outcomes.
That's a huge concern.
It is. Another is data protection. There are strict regulations like the GDPR in Europe and now the AI Act itself that govern how personal data can be collected, processed, and used. The AI Act specifically imposes standards on data quality, representativeness, and the documentation of data used in high-risk AI systems. Businesses need to be incredibly careful here. The key insight is that thinking about data goes beyond just quality and quantity. You must consider its representativeness, potential for bias, and the legal framework.
It's clear that getting the data right is not just a technical hurdle, but also a critical, ethical, and legal imperative. And the book offers a really key piece of advice in this section, doesn't it?
Yes, and it's very practical. The advice is basically, conduct a systematic inventory of all the data your organization collects. Understand what you have, where it comes from, its quality, and crucially, ensure you are fully compliant with all relevant data protection regulations before you even start thinking about using it for an AI project. Get your data house in order first.
Fundamental first step. The chapter then introduces an interesting concept: synthetic data. What exactly is that, and why is it becoming important?
Synthetic data is essentially artificially generated data. It's created algorithmically, but it's designed to mimic the statistical properties and patterns of real-world data.
Why would you use fake data?
Well, it's becoming increasingly important for a couple of key reasons. First, It can help overcome limitations where real-world data is scarce, difficult, or expensive to attain. Second, and very importantly, it can address privacy concerns. It allows AI models to be trained and tested on realistic-looking data sets without needing to use actual sensitive or personal information.
Ah, I see. So you get the patterns without the privacy risk.
Exactly. The book provides a compelling example of autonomous vehicle developers using synthetic traffic scenarios, computer-generated driving situations, to train their AI in a vast range of conditions, including rare or dangerous ones that would be impossible or unethical to test extensively in the real world.
That's a really innovative way to tackle some practical and ethical hurdles. And finally, in this data section, the book discusses data management. It's not just about getting the data initially, it's about managing it effectively throughout its entire life cycle.
Precisely. Effective data management isn't a one-off task. It involves having robust systems and processes in place to organize data from the moment it's collected through its storage, processing, and use, ensuring its accuracy, integrity, and relevance over time.
What does that entail practically?
It includes managing all those different types of data we talked about: training, validation, test data, plus any real-time data streams, and making sure it's accessible, versioned, and documented properly. The book highlights tools like data catalogs that can help improve data discovery, understanding, and consistency across an organization. Ultimately, robust data management is crucial for the long-term success, reliability, and even sustainability of AI initiatives.
So neglecting data management can undermine the whole effort.
Absolutely. The tip here is really about strategy. Develop a clearly structured data strategy before you dive deep into AI projects. Ensure your approach covers how you'll get data that is complete, representative, legally found, and well-managed. That's a cornerstone of any successful, sustainable AI deployment.
A well-defined and actively managed data strategy sounds absolutely essential. Okay, let's shift gears. Chapter 2 then transitions to machine learning, the engine of AI. Why is machine learning considered the engine of modern AI?
Because machine learning, or ML, is really the core technology that empowers modern AI systems to do that crucial thing: learn from data. It allows them to adapt to new situations, make predictions, or derive decisions without being explicitly programmed for every single possible scenario.
So it's the learning part that really distinguishes it.
Yes, it's the fundamental element that distinguishes modern AI from earlier, more rigid forms of artificial intelligence, and certainly from traditional software. It gives AI the ability to improve from experience, in a way, and continuously discover new insights hidden within data.
It's that dynamic capability that makes AI so powerful, handling complexity in ways traditional programming just can't match. And the book emphasizes, coming back to data, that the more relevant and comprehensive the data you feed into an ML system, the better the results you're likely to get.
Absolutely. It's directly linked. The chapter gives an example of a machine learning system used in retail. It could potentially analyze not just historical sales data, but maybe also weather patterns, local events, even social media trends, to identify complex seasonal purchasing behavior, something incredibly difficult, if not impossible, for traditional rule-based software to figure out. The key insight for businesses about ML is this ability to find patterns in large, complex data sets and extract novel insights that can drive much better, more informed decision-making.
The book then breaks down the core principles behind machine learning algorithms. What are they fundamentally designed to do, in simple terms?
At their core, ML algorithms are methodical processes, mathematical procedures really, that are designed to analyze data, identify patterns and relationships within that data, and then use those learned patterns to make predictions or classifications on new, unseen data.
Okay.
The complexity of these algorithms varies hugely, from simple decision trees to incredibly complex neural networks. But the key difference from traditional software remains. Traditional software follows fixed instructions to produce predetermined outcomes. ML systems, on the other hand, can independently discover new patterns and continuously refine their own decision-making logic as they are exposed to more data.
So they're not just executing predefined steps, they're essentially learning the rules, or maybe the patterns is a better word, from the data itself. And there are different categories of machine learning, aren't there, depending on the type of data and how the learning happens.
Yes, the chapter outlines several fundamental approaches. The most common one people start with is probably supervised learning. Here, the algorithm is trained on labeled data.
Labeled meaning?
Meaning the desired output, or the correct answer, is already known for the input data used in training. So you showed lots of emails labeled as spam or not spam, and it learns to predict whether a new email is spam. It's great for making specific predictions or classifications, like forecasting housing prices or identifying faulty products on an assembly line based on labeled images.
Okay, so supervised learning has a teacher providing the correct answers during training. What's next?
Then there's unsupervised learning. Here, the algorithm is given unlabeled data, and its task is basically to find hidden structures, patterns, or groupings within that data on its own without any predefined answers.
Like finding things you didn't know were there.
Exactly. Common applications include customer segmentation, finding natural groups of customers based on their behavior, or anomaly detection, like spotting unusual transactions in financial data that might indicate fraud. The AI explores the data independently.
Interesting. And the third main type?
Reinforcement learning. This is a bit different. Here, an AI agent learns to make decisions by interacting with an environment. It performs actions and receives feedback in the form of rewards or penalties based on those actions. Through trial and error, it learns a strategy or policy to maximize its cumulative reward over time.
Like training a dog with treats.
Kind of, yeah. It's particularly relevant for applications like robotics, where a robot learns to navigate or grasp objects. Or for game playing, think of AI learning to play complex games like chess or Go by playing millions of simulated games against itself.
So supervised learns from labeled examples, unsupervised explores unlabeled data for structure, and reinforcement learns through trial and error with feedback. Are there any other important approaches mentioned?
Yes. The book also touches on some increasingly popular hybrid or related approaches. Self-supervised learning is a clever technique where the supervision signal, the labels, are generated automatically from the unlabeled data itself. For instance, a language model might be trained to predict a missing word in a sentence. The surrounding words provide the context, acting as a kind of self-generated label. This can significantly reduce the need for manual labeling.
That sounds efficient.
It can be. And there's also semi-supervised learning, which tries to get the best of both worlds by combining a small amount of labeled data with a larger amount of unlabeled data. This can achieve good performance with much less manual labeling effort than fully supervised learning, which is really useful in fields like medical image analysis, where getting expert labels is expensive and time-consuming.
It sounds like there's a really diverse toolkit of machine learning approaches, each suited to different kinds of problems and data availability. And the actual machine learning process itself, building one of these models, follows a fairly structured set of steps, doesn't it? It's not just magic.
Not at all. It's quite systematic. The book describes a typical ML workflow that includes several key stages. First, as we discussed, is data preparation, collecting, cleaning, structuring, maybe labeling, and splitting the data into those training, validation, and test sets.
Okay, data first.
Always. Next is model selection, choosing the appropriate type of ML algorithm like a decision tree, a support vector machine, a neural network based on the problem and the data characteristics.
Then the learning part.
Yes. Then comes the training phase itself, where the chosen model actually learns the underlying patterns from the training data. This is often computationally intensive. After initial training, the model is evaluated using the validation data. This helps tune the model's parameters and, crucially, check for and prevent that overfitting problem.
Right, making sure it generalizes.
Exactly. Then the model's final performance is assessed using the independent test data, giving you that unbiased measure of its real-world reliability. And finally, if it passes muster, the trained model is deployed for actual use. And often, it needs ongoing monitoring and potentially continuous adjustment or retraining as it encounters new data over time.
A very systematic and iterative process. And of course, like any complex process, there are various technical challenges that can crop up along the way.
Oh, absolutely. The chapter highlights common challenges. We've touched on ensuring the quality and representativeness of the data that's paramount. Overfitting is a constant concern, making sure the model isn't just memorizing the training data. Its opposite, underfitting, where the model is too simple to capture the patterns, can also happen. Dealing with the scalability and computational demands of training large models requires significant hardware and efficient data management. And then there's the challenge of transparency and interpretability, especially with complex models like deep neural networks. That black box problem makes it hard to trust the output or comply with regulations requiring explainability.
Are there solutions emerging for these challenges?
Yes, the book mentions several. Techniques under the umbrella of explainable AI, XAI, aim to make these models more understandable. Things like federated learning can help train models on decentralized data without compromising privacy. Data augmentation can artificially increase the size and diversity of training data. The key takeaway here is that successfully deploying ML requires not just technical expertise, but also really careful strategic planning, robust data governance, and ongoing management of both the data and the models.
And the tip here.
The tip is practical. For many well-defined business use cases where you have labeled data, starting with supervised learning is often a good approach. And crucially, make sure you regularly validate the performance of your models on new, unseen data to catch any drift or degradation to performance over time.
Solid advice for anyone venturing into machine learning.
Right.
Okay, Chapter 2 then delves even deeper into deep learning and neural networks. How does deep learning build upon that foundation of machine learning we just discussed?
Deep learning is essentially a more advanced and currently very powerful subfield of machine learning. It specifically utilizes artificial neural networks, ANNs, with multiple layers, hence the term deep, to automatically learn and extract increasingly complex patterns and features from large amounts of data, often unstructured data like images or text.
And you mentioned it's inspired by the brain.
Loosely inspired, yes, by the structure and function of the human brain's network of neurons. This approach has been responsible for many of the most significant breakthroughs in AI capabilities in recent years, driving progress in areas like computer vision and natural language processing.
And a key advantage you hinted at earlier is this ability to automatically learn relevant features directly from the raw data, rather than needing humans to manually figure out and engineer those features, which is often required in more traditional ML.
Precisely. That automatic feature extraction, or representation learning, is arguably the defining characteristic and core strength of deep learning. It allows these models to tackle very complex tasks where the relevant features might be incredibly subtle or difficult for humans to define explicitly. Think about identifying a specific person's face in a crowd, understanding the nuances of spoken language, or processing medical images.
So it can find the important stuff on its own. The book gives some typical applications.
Yes. Things like image recognition, facial recognition, object detection in photos or videos, identifying anomalies in manufacturing, medical diagnostics, analyzing X-rays, MRIs, or pathology slides to help detect diseases like cancer earlier and more accurately, and speech analysis and processing, not just transcribing speech, but understanding intent, detecting emotions in customer service calls, powering sophisticated voice assistants. The key capability driving these is that autonomous feature extraction from raw, complex data.
An impressive range of applications. The chapter then explains the basic structure and functionality of these neural networks. Can you give us a simplified overview of how they operate? Not too technical.
Okay, I'll try. At its core, a neural network is made up of multiple interconnected layers of simple processing units, often called artificial neurons or just nodes. They work together to process information step by step.
Layers? What kind of layers?
Typically, there's an input layer that receives the raw data, like the pixels of an image or the numerical representation of words. Then there are one or more hidden layers sandwiched between the input and output. This is where the actual analysis and pattern recognition happen. Early hidden layers might identify simple features, like edges or corners in an image, while deeper layers combine these to recognize more complex patterns, like shapes, objects, or faces. The presence of multiple hidden layers is what gives deep learning its name.
And the final layer?
Finally, there's an output layer that takes the processed information from the hidden layers and produces the final result. Maybe a classification, for example, cat or dog, a prediction, for example, future stock price, or some other form of output.
And each neuron within these layers has a specific job in processing the information.
Sort of. Each neuron receives input signals from neurons in the previous layer. It multiplies these inputs by associated weights. These weights are the parameters the network learns during training, indicating the strength or importance of each connection. The neuron then sums up these weighted inputs and passes the result through an activation function. This function introduces nonlinearity and determines whether and how strongly the neuron's signal should be transmitted to the neurons in the next layer. It's the nonlinear activation functions that allow the network to model complex, real-world relationships in the data, not just simple linear ones. Think of a network analyzing skin images for cancer. It learns complex visual patterns through this layered, weighted, activated processing.
It sounds like a complex chain of interconnected calculations, each contributing a small part to the overall understanding. The book discusses backpropagation as the fundamental learning mechanism. That sounds quite technical. Can you give us a conceptual handle on how it works?
It is a core concept, but we can think about it intuitively. Backpropagation, short for backward propagation of errors, is essentially the algorithm neural networks use to learn from their mistakes and improve their performance during training.
How does it know it made a mistake?
Well, first, the network makes a prediction based on some input data. That's the forward pass. Then, this prediction is compared to the actual correct answer, which you know because you're using labeled training data. The difference between the prediction and the truth is the error.
Okay, so it calculates the error. Then what?
Then, this error signal is propagated backward through the network, layer by layer. Calculus is used to figure out how much each connection weight in the network contributed to that overall error.
Assigning blame, sort of?
Exactly. Based on how much blame each weight gets, the weights are adjusted slightly, typically using an optimization algorithm like gradient descent in a direction that should reduce the error next time that input, or a similar one, is seen.
So it nudges the connections to be better next time.
Precisely. This whole process, forward pass, calculate error, backward pass, adjust weights, is repeated thousands or even millions of times with large amounts of training data. Gradually, the network's weights are tuned until its overall error rate is minimized, and it becomes good at making accurate predictions. Think of it like tuning a complex musical instrument by making tiny adjustments until it sounds right. Backpropagation is the process of making those tiny adjustments to the network's tuning.
So it's a process of making a guess, seeing how far off it is, calculating who was responsible, and then subtly adjusting the
Then there's the persistent black box problem. The sheer complexity of deep networks with millions or billions of parameters makes it very difficult to understand exactly why a particular decision was made. This lack of transparency is a major hurdle for trust and regulatory compliance, especially in high-stakes areas.
And data dependency.
Yes, deep learning models are typically very data-hungry. They need extensive, high-quality data sets to learn effectively. Getting enough suitable data can be a major bottleneck.
Are there ways to mitigate these challenges?
There are ongoing efforts. As mentioned, explainable AI, XAI techniques are being developed to shed light on model decisions. Researchers are working on more efficient network architectures and training methods to reduce resource consumption. And techniques like data augmentation, artificially creating more training data, and transfer learning, reusing parts of pre-trained models, can help address data scarcity.
So work is being done.
Absolutely. But the book also makes a pragmatic point. For applications that carry high risk under the AI Act, where traceability and transparency are paramount, using hybrid models, or perhaps simpler, more interpretable machine learning models, might actually be a better strategic choice, even if they offer slightly lower performance, just to ensure regulatory compliance and understanding.
That's a really important consideration, balancing performance with transparency and risk. And the tip here relates to pre-trained models.
Yes. The tip is practical. Consider starting with pre-trained neural networks where possible. Many organizations make powerful models available that have already been trained on vast data sets. You can often fine-tune these for your specific task, which can save significant training time and resources. But, the tip adds, always carefully evaluate the performance and the transparency of any deep learning model you deploy, especially if using a pre-trained one where you didn't control the initial training.
Important practical advice for anyone leveraging deep learning. Okay, the next section in Chapter 2 moves us right to the cutting edge: transformers and large language models. These have absolutely exploded into public consciousness recently. What makes them such a significant advancement over previous AI models?
Well, traditional neural networks, particularly recurrent neural networks, RNNs, that were often used for sequential data like text, had limitations. They processed data step by step, which could be slow, and, more importantly, made it difficult for them to capture long-range dependencies, understanding how words at the beginning of a long paragraph relate to words near the end. They could sort of lose the context.
They had short memories, in a way.
Kinda, yeah. Transformer models represent a major breakthrough because they use a novel architecture based heavily on something called the attention mechanism that allows for parallel processing of the entire input sequence simultaneously.
Parallel processing, so they look at everything at once.
Essentially, yes. Instead of reading word by word, it's more like skimming the whole text at once to understand the relationships between all the words. This makes them much faster to train and, crucially, much more effective at capturing context and understanding relationships between elements, even if they are far apart in the sequence.
And the book highlights a key research paper from 2017 that introduced this.
Yes, the highly influential paper titled "Attention is All You Need," published in 2017 by researchers at Google. It introduced the transformer architecture, and it really has had a profound impact on AI research since then. It's become the foundation for many of the most significant advancements we've seen recently, particularly in natural language processing.
And this transformer architecture is the underlying technology behind these large language models, or LLMs, that everyone's talking about, things like ChatGPT.
Exactly. Large language models are probably the most prominent application of the transformer architecture. They are neural networks, specifically transformers, that have been trained on absolutely massive data sets of text and code, sometimes encompassing a significant portion of the internet.
Wow. What does that training allow them to do?
This vast training allows them to not only understand and interpret human language, but also to generate it autonomously with remarkable fluency, coherence, and contextual relevance. LLMs excel at a wide range of complex linguistic tasks: translation, summarization, question answering, content creation, often with impressive accuracy. That parallel processing capability of the transformer architecture is what enables them to handle such enormous data sets during training and capture those intricate contextual relationships within language so effectively.
The chapter breaks down the basic transformer architecture into two main components, the encoder and the decoder. Can you explain the primary role of each of those?
Sure. In the original transformer architecture, particularly for tasks like machine translation, you have these two parts. The encoder is primarily responsible for analyzing and understanding the input data. So if you give it a sentence in English to translate, the encoder processes that sentence, figures out the meaning of each word, and importantly understands the relationships between those words, the context. It creates a rich numerical representation of that input.
Okay, so the encoder reads and understands. What does the decoder do?
The decoder then takes that encoded representation from the encoder and uses it, along with the context that is generated so far, to generate the desired output sequence, step by step. In the translation example, it would generate the translated sentence in, say, French, word by word, paying attention to the meaning captured by the encoder. Some models, like GPT, are primarily decoder-based, focused on generation, while others, like BERT, focus more on the encoding or understanding part.
So, encoder for understanding, decoder for generating. And a core innovation within this architecture is that attention mechanism you mentioned. What is the fundamental idea behind attention? Why is it so important?
The attention mechanism is really the secret sauce, the cornerstone innovation that gives transformers and LLMs their power. It allows the model, as it processes the input sequence or generates the output sequence, to dynamically weigh the importance of different parts of the sequence relative to the current word or task it's focusing on.
Can you give an analogy?
The book uses a good one.
Yeah.
When you read a sentence, you intuitively pay more attention to the key words that carry the most meaning for understanding the overall point. The attention mechanism allows the transformer model to do something similar mathematically.
How does it work, roughly?
Roughly, for each word or token it's processing, it calculates attention scores that represent how much focus it should put on every other word in the sequence, including itself. Words that are highly relevant to understanding the current word get higher attention scores. This allows the model to draw context directly from the most relevant parts of the input, even if they're far away. It's what enables them to capture those long-range dependencies that RNNs struggled with.
And the book mentions multi-head attention.
Yes, that's another refinement. Instead of having just one attention mechanism, multi-head attention uses multiple attention heads operating in parallel. Each head can potentially learn to focus on different types of relationships or different aspects of the input sequence simultaneously, like one head focusing on grammatical structure, another on semantic meaning. This gives the model an even richer understanding of the context.
It sounds incredibly sophisticated that this attention mechanism seems key to why LLMs can generate such human-like text. The chapter also discusses some prominent examples like GPT and BERT. What are the key characteristics or maybe differences between them?
Right, they represent slightly different philosophies built on the transformer base. GPT, developed by OpenAI, the architecture behind models like ChatGPT, is particularly known for its strong capabilities in generating coherent and contextually relevant text. It excels at tasks like continuing a piece of text you provide, answering questions in a conversational manner, summarizing documents, and even creating original stories or code. Its training on vast text data makes it very good at predicting the next word in a sequence, enabling it to generate long, complex, and often creative outputs.
So GPT is really strong on the generation side. What about BERT?
BERT, developed by Google, stands for Bidirectional Encoder Representations from Transformers. Its key innovation was its ability to understand the meaning of words by considering their full context, looking at the words both before and after a target word simultaneously during training. This bidirectional approach makes it particularly effective for tasks that require a deep understanding of the nuances of language meaning within a given context.
Like what kind of task?
Things like sentiment analysis, is this review positive or negative? Question answering, finding the specific answer within a passage, and text classification. BERT is often used under the hood in search engines, for example, to better understand the intent behind your search query. So simplistically, you could say GPT is more focused on generating text, while BERT is particularly strong at understanding the meaning embedded within text.
Generation versus comprehension, broadly speaking. And transformers aren't limited to just text, are they? The book mentions multimodal transformer models. What can those do?
That's right, the architecture is proving remarkably flexible. Multimodal transformer models are designed to process and understand information from different types of data, different modalities simultaneously.
Like text and images together.
Exactly. The book highlights examples like CLIP from OpenAI, which learns the relationship between images and their textual descriptions. You can give it an image, and it can find the best text description, or vice versa. And Delay, also from OpenAI, which can generate entirely novel images based purely on textual prompts. You give it, like, draw a picture of an astronaut riding a horse. These models showcase the power of the transformer architecture in bridging the gap between language and vision.
It's fascinating how these models are learning to connect different forms of information. The chapter concludes its discussion of transformers and LLMs by touching on their wide range of applications and their overall significance, but also some of the challenges they pose for businesses.
Yes, the applications are rapidly expanding, as we've seen, across text processing, translation, chatbots, summarization, content creation, image and video processing, generation interpretation, and the development of sophisticated multimodal systems, linking language and visuals for things like personalized recommendations or interactive marketing.
But there are hurdles for businesses using them.
Definitely. The book points out important challenges businesses need to consider. Data privacy remains a concern, especially regarding the data used for training these massive models or data submitted by users interacting with them. The lack of transparency, that black box effect, could be even more pronounced with these incredibly complex models, making it hard to ensure fairness, accountability, or compliance. And the potential for generating misinformation or biased content is also a significant risk that needs careful management.
So, powerful tools, but they come with responsibilities. What's the practical tip here?
The tip is to perhaps start by exploring established open-source transformer models first. There are many powerful models available that you can experiment with and adapt. But crucially, you need to rigorously evaluate their performance, limitations, and potential weaknesses for your specific use case before deploying them, especially in sensitive applications. And as mentioned before, the chapter reminds us of the significant economic and ecological considerations due to the immense computational resources needed to train and run these very large models. It's not a trivial undertaking.
Really important practical and ethical factors to keep in the front of your mind as these powerful technologies become more widespread. Okay, finally, Chapter 2 concludes with a discussion of something fundamental but often overlooked: hardware and infrastructure. Why is the underlying hardware such a critical piece of the AI puzzle?
Because ultimately, the performance, efficiency, scalability, cost, and even sustainability of any AI system are fundamentally tied to the hardware and infrastructure it runs on. You can have the most brilliant algorithm, but if the hardware can't keep up, it won't deliver. A well-designed and appropriate infrastructure is absolutely essential.
The book outlines various hardware options, starting with the workhorse, the central processing unit, or CPU. We all have those in our computers. When is a CPU generally sufficient for AI tasks?
CPUs are designed to be versatile, with a few very powerful cores optimized for handling a wide range of tasks, particularly those involving sequential computations. They're generally sufficient for running simpler AI models, or for the initial stages of prototyping and development where the computational demands aren't extremely high. But for the highly parallel computations required by many modern AI tasks, especially deep learning, CPUs often become a significant bottleneck. They just can't do enough things at once.
Which leads us to graphics processing units, or GPUs, which are almost synonymous with AI training these days. What makes them so suitable?
GPUs were originally designed for rendering graphics in video games, which involves performing similar calculations on large amounts of data, pixels, in parallel. It turns out this architecture, with thousands of smaller specialized cores, is incredibly well suited for the kinds of matrix multiplications and other parallel operations that are fundamental to training deep neural networks and processing large datasets in AI.
So they're much faster for those specific AI tasks.
Significantly faster, yes. They've become the standard for training complex models in areas like image recognition and natural language processing. The downside is that powerful GPUs tend to consume a lot more energy and can be considerably more expensive than CPUs.
Makes sense. The chapter also mentions accelerated processing units, or APUs, and neural processing units, or NPUs. What are these, and where do they fit in?
Okay, so an APU essentially integrates a CPU and a GPU onto a single chip. They offer a more energy-efficient solution compared to having separate high-power CPU and GPU components, making them suitable for tasks involving a moderate amount of parallel processing, often found in laptops or in some edge AI applications where power efficiency is important. They might not match the raw power of a dedicated high-end GPU, though.
And NPUs, neural processing units.
NPUs are even more specialized. They are processors designed specifically to accelerate the computations involved in running neural networks. They are highly optimized for AI workloads, offering potentially very high performance with relatively low energy consumption. This makes them increasingly common in mobile devices, like smartphones for running on-device AI features, in edge AI devices for real-time processing, and in applications like efficient speech recognition. Their specialization means they might be less flexible than GPUs for other types of computation, though.
So the choice really depends heavily on the specific AI application and its unique computational needs: speed, power efficiency, flexibility. Beyond these more general types, there's also even more specialized hardware mentioned, like VPUs, FPGAs, and TPUs. Briefly, what are they good for?
Right, these are even more tailored. VPUs, vision processing units, are, as the name suggests, highly energy-efficient processors, specifically designed for accelerating computer vision tasks, often deployed on edge devices like smart cameras. FPGAs, field programmable gate arrays, are interesting because they offer a high degree of flexibility. Their internal logic can be reconfigured after manufacturing to suit specific AI algorithms, making them valuable for research or rapidly evolving industrial applications. And TPUs, tensor processing units, developed by Google, are custom-designed hardware accelerators specifically optimized for deep learning workloads, particularly those using Google's TensorFlow framework. They excel at the specific mathematical operations, tensor operations, common in neural networks.
Wow, quite a landscape of different processing options, each optimized for different aspects of AI. The book then discusses a really important strategic decision: whether to deploy AI systems using cloud-based infrastructure or on-premises solutions. What are the key factors organizations need to weigh here?
This is a major decision. Cloud computing, using providers like Amazon Web Services, AWS, Microsoft Azure, or Google Cloud Platform, GCP, offers the big advantage of accessing powerful and crucially scalable hardware resources over the internet on demand.
Pay as you go.
Largely, yes. This provides flexibility. You can scale up or down as needed. It often means lower initial cost because you don't have to buy expensive hardware up front. And cloud providers offer a huge range of pre-trained models, managed AI services, and specialized hardware like TPUs that might be hard to acquire otherwise.
Sounds pretty good. What are the drawbacks?
Well, you become dependent on a third-party provider. There can be data privacy and security concerns, especially if you're dealing with highly sensitive data. Where is it being stored and processed? And while initial costs might be lower, very intensive long-term usage can potentially become more expensive than owning the hardware. You're paying for compute times, storage, data transfer, managed services.
Yeah.
It adds up.
Okay, so what about the alternative, on-premises?
On-premises solutions mean the company owns and operates its own hardware infrastructure locally, in its own data centers. The big advantage here is full control over your data and security, which can be absolutely critical for highly sensitive applications, like in healthcare or finance. It can also be more cost-effective in the long run if you have very high, predictable usage, and you avoid dependency on external providers.
But the downsides?
The main drawbacks are the high upfront investment required to buy and set up the hardware, and the limited scalability. If your needs suddenly spike, you can't just instantly provision more resources like you can in the cloud. Maintenance and upgrades are also your responsibility.
So cloud gives flexibility and lower startup costs. On-prem gives control and potentially lower long-term costs for heavy users. Is there a middle ground?
Yes, and many organizations are opting for hybrid strategies. This involves blending cloud and on-premises infrastructure. For example, you might keep highly sensitive data and critical core operations running on your local hardware for maximum security and control, while leveraging the scalability and specialized services of the cloud for less sensitive data processing, model training, or bursting capacity when needed. This aims to strike a balance between security, scalability, cost-effectiveness, and flexibility.
It sounds like a hybrid approach could offer a good practical balance for many organizations navigating this. Finally, the chapter touches on a topic that's becoming increasingly important: sustainability and energy efficiency in AI infrastructure.
Yes, this is a really significant issue. The immense energy consumption associated with training and running large-scale AI models, especially deep learning models, is a growing concern. Both from an environmental perspective, think carbon footprint, and an economic one, electricity costs money.
Is it really that energy intensive?
It can be shockingly so. The book mentions studies estimating the significant CO2 emissions associated with training just one very large language model. As AI becomes more widespread, companies are increasingly being held accountable for adopting sustainable practices and reporting on their environmental, social, and governance (ESG) performance.
So what can be done to make AI more sustainable?
Several strategies are discussed. Using more energy-efficient hardware, where appropriate maybe those specialized MPUs or FPGAs for specific tasks, instead of power-hungry GPUs for everything. Choosing cloud providers that are committed to using renewable energy sources for their data centers. And, importantly, focusing on model optimization, developing techniques like pruning, removing unnecessary parts of a neural network, or creating more parameter-efficient models that achieve good results with less computation.
Does geography play a role?
It can, yes. The book points out that the physical location of computing resources in data centers impacts energy costs and the sustainability profile, depending on local electricity prices and the energy mix, how much comes from renewables. Regions offering affordable and sustainable energy can provide both economic and ecological advantages for large-scale AI operations. Ultimately, the goal is to align ecological and economic interests for the long-term viability and acceptance of AI.
And the tip here relates back to the infrastructure choice.
Yes. The tip suggests carefully evaluating a hybrid infrastructure strategy and potentially keeping critical data and core AI functions local, on premises, where feasible and appropriate. This can offer greater control over data, potentially reduce long-term operational costs compared to constant heavy cloud usage, and give you more direct oversight of the energy consumption and environmental impact of those core functions. It's about making conscious choices.
A really vital consideration as AI continues to evolve and scale up. Well, we have certainly covered a tremendous amount of foundational ground in this deep dive into Chapter 2 of AI Act Competence Plus Compliance.
We really have. It's packed with essential concepts.
It's clear that getting a handle on these fundamentals, from the basic definitions and history, through the crucial role of data, the mechanics of machine learning and deep learning, the power of transformers and LLMs, right down to the hardware, is absolutely essential for anyone looking to really understand and navigate the world of AI. Particularly, as you said, in the context of the upcoming European regulations. Hopefully, this discussion has provided you, our listeners, with a much clearer understanding of these core building blocks.
Definitely. This chapter truly provides that solid, essential foundation. And as the book progresses in later chapters to explore the specifics of the European AI Act, the legal frameworks, the risk management strategies, how to build the necessary competencies within your organization, having this fundamental knowledge of what AI is and how it works will be absolutely crucial for engaging effectively and ensuring compliance. You can't regulate what you don't understand.
So true. And we really do strongly encourage you to explore Marcus M. Kirchmeier's comprehensive book further. Again, it's called AI Act Competence Plus Compliance Fundamentals of Artificial Intelligence and its Safe Use in the European Union. You can find it in bookstores and online at aac-book.eu to continue your journey into these critical areas.
It's a valuable resource for sure.
Absolutely. And maybe a final thought for you to ponder as you continue navigating this space, reflecting on all these fundamental components, the data, the algorithms, the hardware. Which aspect do you think presents the biggest practical challenge for businesses trying to implement AI responsibly right now? Is it getting the data right? Understanding the algorithms, managing the infrastructure, something else entirely? It's worth considering where the real friction points are for you and your organization. Thanks for joining us for this deep dive.